Welcome to another Refrigeration Mentor podcast and another CO2 Monday. I'm your host, Trevor Matthews. And today I have another great guest who was actually on in, I believe, a week 6 or 7, Wynand Groenewald from Future Green Now, or FGN. This guy is a global expert on CO2. I love having conversations with him. I always learn. Every time I have a conversation, I'm learning something. So this is why I do these, is to share the knowledge with you as well as I can learn, because we're getting into designing and engineering of CO2 systems. And I'm still a novice at this, to be honest with you. I've been to a lot of courses about design and engineering, but I'm still learning just like all of you. And today is going to be such a great conversation. Welcome, Vinan. How you doing?
Good, thanks, and you. Good to be back again. Thanks for having me.
And I'm doing awesome. I'm awesome to be here. I want to thank everyone for showing up and coming to hang out. If you have questions, this is a live recording on Zoom. And for those who listen on the podcast, always leave a review, share this podcast if you like it. And if you have any questions here, and this is why I love the live stuff, we get questions and really good questions week over week. So use the chat box. If you want to unmute yourself, we can do that at the end. Today, we're going to get into designing and engineering. But first, Vanya, why don't you do a quick introduction of yourself and your company to let everybody know?
Sure, thanks. So as you mentioned, I'm Wynand Groenewald, and basically my company, Future Green Now, based in South Africa but operating internationally, is a refrigeration consultation company based, or how can I say it, specializing and focusing on natural refrigerants, so ammonia, CO2. So that's really kind of what we grind our teeth into and what we offer, and that offering includes product development, um, industrial refrigeration system design, pipe scheduling, pipe design. So I guess today, what I want to touch on to is some tools and some stuff that can be used, especially when we're looking at product development and more into the detail of the CO2 design. And it's more just actually not about as much as you can utilize that tool to design a certain product or installation or type of system, but it's what you can learn out of seeing that. I mean, that's one of the main things that I think myself and my team like to utilize the software and the programs that we're going to showcase a little bit. It's as you figure it out, you learn the soft details behind everything else, and that gives you more and more better understanding of how a system sometimes can operate.
Yeah, we had Damon Reed on last week from Pro Refrigeration, and he said you guys were just phenomenal helping them out to get their first CO2 transcritical chiller off the ground, the first one in North America, I believe. So that was such a great conversation. And this is some of the stuff FGN is doing, helping companies like that expand into the CO2 market. So that's super exciting. So awesome. Well, why don't we just dive right into it and get into some of this designing and engineer, because I even know there's a few people on the call that reached out to me last few weeks asking me some questions on design and engineer, and I wasn't 100% sure on the answers, So I'd love to get into some of those. But why don't we just start off with some of the slides that you have, maybe?
Cool,
And for those who,
definitely. And
yeah, cool.
yeah, go for it. No,
Yeah,
no,
for
carry on.
those who are listening, we'll do our best to walk through any of the slides or the software and let you know the name of that software.
Yeah, no, I'll do my best to describe for the non-visual guys. Yeah, definitely. I mean, thanks for, again, like I said, thanks for having me. And also, if there is anytime, feel free to stop me if there's questions or anything that you want to do. So I'll try and start sharing my screen here. Let me know if you can see that.
Yeah, it's not in full screen. So
Yeah, now I think what I'm going to do is I'm just going to jump on to basically so basically the program that we're going to look into a little bit is called basically Engineering Equation Solver, or the abbreviation is EASE. So this basically is a refrigeration tool that has certain functions built into it. Functions like what you can utilize pressure and temperature of, and you can determine enthalpies, entropies, qualities of refrigerant and stuff like that. So I mean, it's got built in, it many types of, almost all the refrigerants are built into this program. So basically what you can do is you can write your program logic, and you can tie everything together. So if you make changes on it from a saturated suction point of view, you can see the effect it will have on a compressor or the discharge temperature. I mean, you can go into as little detail as you want or as much detail as you want. So typically would do just a simple, straightforward, how can I say it, what's the correct word now? Sorry, now I'm slipping my, now I'm losing my ability to talk. No,
That's all
so
good.
basically, yeah. So I mean, your non-dimensional stuff, like you can allow anything. What I'm trying to say is you can allow pressure drops and incremental intervals throughout the heat exchanger. For argument's sake, you can typically take a heat exchanger and break it down into 1,000 increments if you want, and see how the refrigerant will change through every little increment throughout the heat exchanger. I mean, that's the level of detail you can go into, or you can literally just do a point-to-point basis where you go and say, you know, you have an expansion device, so you go from pressure X to pressure Y, your quality of your refrigerant will be this, your temperature will be that, your density and enthalpy. So you can do a basic system analysis that you can do with that. So I mean, without going into the detail of it, so basically, as you can see, you can follow and determine what the mass flows will be of the system, how much of that is liquid, how much of it is flash gas. That will be out of your receiver. In this, I think it's this particular one. So for argument's sake, we have implemented the Doran compressor polynomials. So what you can do is you can utilize software, either the Bitzer or Doran's or any type of compressor you can use. You can pull the polynomials. Those polynomials have been put together to basically suggest or showcase a compressor within its compressor envelope. So if you utilize the polynomials and you write your program according to the polynomials, so basically you can change your evaporating temperature, your condensing temperature, all your parameters around it, receiver pressure, all of that you can change, and you can see what the effect is on the system. So I mean, this is the background of it. If you want to, you can pull out the front screen of it, and then basically you can go and say, like, okay, for argument in this stake, for those compressors that you have implemented, you can choose evaporating temperature of, let's say, 23F, which is minus 5C. You can associate that with a certain discharge pressure, a certain receiver pressure, and then obviously a certain gas cooler outlet temperature. That usually is your main functions that you want to put in. And then when you calculate that, you can see the effect that will have on your system. So the reason why I pulled this up is I thought maybe today we can touch a little bit on heat reclaim and utilize this tool or
Yeah.
showcase a little bit of the heat reclaim side of life off of it. So,
Yeah.
I mean,
Sounds
I
great.
can
One thing, Vinen, why
yo,
don't you explain polynomials to the audience? Because some people will know that, some people not. When you explain and mention,
hmm.
you can put the polynomials in.
So basically polynomial is, I guess I'm trying to, the most layman way to explain it is you've got a very long, how can I say it, formula that will give you, like the one formula will give you the power output of the compressor according to certain inputs. And that input will be, for argument's sake, the condensing pressure of that system versus the evaporating temperature of that system. And according to polynomials that has been determined from designing a compressor and operating a compressor within its how can I say it, operating envelope.
Yeah.
So let's put it this way: in an envelope, you can dot down perhaps 10, 20, 30 lines, and a polynomial is exactly what it is. You draw a polynomial line throughout all these, and a polynomial curve throughout all these lines that's been physically measured. And at the end of the day, you know, you can interpolate and get that basically every incremental or every new evaporating temperature and every new condensing temperature will follow that polynomial curve and give you the output according to that. So
Yeah.
in
Thank
a
you.
nutshell, that's
Yeah. No, that was
what you
perfect.
use
Bang
that
on.
for.
Because I know the first time that I think it was a couple of years ago, the first time you said that, I'm like, what is he talking about? Because I didn't know. And I went and looked it up. So thank you for explaining that.
Sure, no problem. So I ran a few things around the heat reclaim, as I said before, so I can just maybe run through that.
Yeah.
Um, so it's also heat reclaim and it's also condensing. So basically one thing that you can understand and what I'm trying to say is like there is, again, it comes to the pressure temperature correlation, or the lack of pressure temperature correlation when you're working in your transcritical or above critical point and your subcritical point. So I mean, these are kind of questions that do come around our way more often than none. Is, you know, the difference in gas cooler selection, the difference in heat reclaim, you know, why do you get a certain approach when you're operating in subcritical condition versus having a certain approach when operating in transcritical conditions. So that's kind of the one thing. And then the one thing I also want to kind of like, let's call it a myth buster, is the whole heat reclaim kind of thing, to force and when to force and how to force, and why we say you must force or can force your system to operate transcritical, even if it's in the middle of winter and you're operating at a very low subcritical factor. Like, what is the benefit of forcing yourself into transcritical to get that heat out of your system, without having an additional secondary heat pump or gas source or any other type of heat source around that? So that's kind of the things that I thought we can touch on, and I'll try and showcase a lot of that as much as I can through the programs, or if anybody has questions.
Yeah, because that was
Um,
one thing that would really caught me off the first time I've heard of that. Because I was talking to a buddy, he's like, it was the middle of winter. This is in Canada. In the middle of winter, it's cold. He's like, yeah, my system's running transcritical right now. I'm like, well, isn't it supposed to, the lower condensing, lower, compression ratio is always better for a compressor, but it depends. It all depends. So what's the
mm,
cost of that fuel, like that heating source, compared to using it in transcritical? So, and that really kind of blew my mind that CO2 is so versatile that it can do both all at once. When you think about refrigeration, I didn't always think about heat, because when I did heat, it was natural gas.
mm,
I didn't think of heat as a refrigeration, but people in the heat pump industry and stuff will really understand that more than me. But that's really what took me
yeah,
off when I heard transcritical in the middle of winter.
yeah, and I mean, and again, what you need to understand with transcritical in the middle of winter, it's there's a difference between the efficiency of a system by being forced naturally, which your system is going transcritical because it can't reject its heat because of high ambient conditions, or compared to, you are still rejecting your heat, but you're just forcing your system to go transcritical. I mean, the loss of efficiency is much less than having to go transcritical because of not rejecting your heat. So that's the one thing I will touch on as well, or try to showcase and explain. Um, so number one, so yeah, I mean, just this I'm sure if everybody sits in your talks, this would be knowledge by now. But yeah, subcritical operation of a gas, because of argument's sake, you're condensing and you have a pressure temperature correlation, so you can't beat the laws of nature. So your typical HFC based refrigeration systems, you will, once you go under your subcritical or your condensing, always you'll be having a phase change that's correlated, where a certain temperature matches a certain pressure. It's like boiling your kettle. You will have the same temperature water until all the water has evaporated, or turned into steam. That's the same effect you have in your condenser. Um, so if you look at the gas cooler and what can be deemed as the approach across a gas cooler, is when we speak to a gas cooler, or when we speak to a condenser, we refer to the pinch point at the start of the condensing process, versus the air going on to that. So basically, um, your ambient air temperature where you start versus your straight line. So if you follow here, you're looking at your line here, and you're looking at how your air follows over that condenser while you are condensing your refrigerant. So you can't have your air go closer than what you can get that approach, where you basically can see that's your desuperheating. And once you have finished desuperheating, you start condensing and you kind of start following a straight line. So your air can't approach closer than that line, which is deemed, which is deemed your pinch point, but your approach is basically your initial air temperature onto your condenser versus what you are condensing. So when you refer to a supplier, or you refer to, like, I want a certain approach over my condenser, basically what you're saying is, I want to get my air temperature and my condensing temperature as close to each other as possible, but it's only physical to get as close in a certain way. When you look at CO2 in a transcritical manner, again, like we said, is you have no pressure temperature correlation, but also what you get is you have a constant pressure, but you're continuously rejecting heat. So your temperature through your gas cooler is continuously reducing its own temperature. It doesn't reach a straight line where you are changing the phase of the refrigerant. So your approach is your gas cooler outlet temperature versus your ambient onto your gas cooler. So if you look at the same ambient line in transcritical mode, you can see that your ambient line can have a much quicker approach, or can be allowed to absorb more heat fairly faster than it can do in a condensing manner. So your pinch point is, or your approach, what you refer to in a transcritical gas cooler versus CO2 condenser even, is much lower than what you would be able to do when you're condensing. So typically, I mean, if you're going to size a condenser to operate in a subcritical manner, or operate as a condenser, you're going to probably allow anything from, I would say, 8 to or 10 to up to 18F, where in transcritical mode you can allow for as close as a 4F approach, and even a little bit lower if you want to be very aggressive.
So Vine, and just so I know, and I'm hearing you correct. So the gas cooler inlet versus the ambient is that pinch point. Is that correct?
The gas cooler, in transcritical mode, the gas cooler outlet temperature
Yeah.
compared to what the ambient temperature onto the gas cooler, that's your
Approach.
approach.
That's your approach.
Yeah.
So the pinch point again. So your approach is your gas cooler outlet versus your ambient. That's your approach. But the pinch point, how do I calculate that again? Or can I?
Well, your pinch point, yeah, well, you can utilize, that's where we can utilize engineering equation solver to determine
Okay.
that.
Okay.
But basically, your pinch point would be the closest point of your air versus your CO2. So that's why we say
Okay.
in condensing, that pinch point will be where you stop desuperheating. So once you start condensing, that and according to your ambient, that's your pinch point, but that
Uh,
doesn't determine your approach.
okay.
It just
Totally.
means you have I mean, you can't, if you're condensing at, I don't know, 15C, and your ambient can't be 15C.
Yeah. Makes
You
sense.
can't transfer
Yeah.
heat anymore. So your
Yeah.
pinch point is how good you can reject heat and how close that can get to each other.
Okay,
Um,
perfect. I totally understand that now. How about so the lower the approach, the more efficient that gas cooler will be? Is that if I am I
not
correct saying that?
not your gas cooler, but
Okay.
typically at the end of the day, your refrigeration system. Because
Okay.
again, if your approach, the bigger your approach is, um, your ambient stays constant, but your discharge pressure and temperature will have to increase.
Mm,
Um, so if you have a very large approach, it means that you typically, if you want to put it in practical terms, you're going to end up with a small gas cooler, which means you're going to struggle to reject your heat,
yeah.
which means the only way you can do that is you're going to end up with a system running at a higher condensing pressure than it can. Um, so
So
that's one of the benefits that we say. And I mean, from a control point of view, again, when you start looking at transcritical operation, is, I mean, that comes down to maybe another topic where you have in your software, you have your transition zone and how you have your optimum discharge pressure versus gas cooler outlet temperature. And I mean, one of those things that you need to consider, or what the software developers need to consider, is, if you have a certain approach, so a certain ambient temperature is going to give you a certain condensing temperature when you're in subcritical let's say that's 12F approach. So there's a 12F difference between what you're condensing at and what the ambient temperature is. Once that system pops into transcritical mode, that approach all of a sudden becomes 4F. So you now reduce that. So you must make sure that you firstly, from a control logic point of view, don't reduce fast enough that you bounce yourself back into subcritical mode, just to have an increase approach again and want to pop yourself back into transcritical mode again. So that's where I think a lot of that's where I guess at the end of the day, the logic that's behind the operation of a transcritical system is sometimes a bit more complicated than what we give it credit, I guess,
Yeah.
some days.
Yeah, no, for sure. Because I've seen that working on the demo trainer that I worked on when I worked at Emerson doing all these trainings. I seen where when it went into, because there's two different logics. When it's in transcritical mode, that high pressure valve is working one way. When it's in subcritical mode, it's working in another way. So when you're in subcritical, you're monitoring subcooling at that point. But when you're right at that just that point when it's 87.8, you don't want it just to kick over and then it all of a sudden 80.7 it kicks back into subcritical because your valve will be just all over the place. So there's like a little bit of time delay in there because I see it go up over 87.8 and then it'll be 88 and then 88.2 or 31 Celsius and 32 Celsius and then it kick over after a time like a specific time period so you don't start hunting that valve and it's all over the place.
Yeah, no, exactly. And it's what you call, I think they refer to it in some cases like the transition zone.
Yeah.
Like there's almost a dead band where you won't operate, and that's basically just below or just above your critical point. I mean, that's also once you go into once you go into, and that's also another topic, but once
Yeah.
you go into transcritical mode, there's a reason why your minimum discharge pressure is 75 bar. Because number one, if you're going to be right at that transcritical point, your temperature lines become very flat. So one C or 2C becomes a very big, to reduce your gasket outlet temperature, another 1 or 2 degrees C or 2 or 3 degrees F, all of a sudden becomes a big chunk of capacity where you need to like lift yourself just a little bit above that critical pressure so that your line starts bending a little bit, if I can
Yeah,
put
yeah,
it that way.
yeah,
Because to get over that flat line is a massive capacity. I mean, that comes down again to mechanical subcooling in a certain sense. Like a lot of times there's a confusion that you want to implement mechanical subcooling or some form of subcooling at the end of the day, and people want to implement that to try and reduce the discharge pressure of the system. But technically, you don't want to reduce that discharge pressure all the way to whatever your new gas cooler outlet temperature is, just because the more you reduce your discharge pressure, the more capacity you require from your mechanical subcooler. Because the more you drop that pressure, like if you're taking yourself from 38C down to 32C, that can be maybe 100 kilowatts of mechanical subcooling. You drop the discharge pressure, and you're still trying to do 38C to 32C. All of a sudden, you require maybe 250 kilowatts to do that same mechanical subcooling. So you want to make sure where you control your system, at what actual temperature you control it. And get your efficiency out of the subcooling that your mechanical subcooler creates, rather than trying to get your efficiency by reducing the discharge pressure. Otherwise, you start again you start putting additional power into whatever is your mechanical subcooler. That kind of goes
yeah,
against what you're trying to achieve.
yeah, exactly. I love this. I love this. Learning so much.
So that's basically just also wanted, like I said, that was to showcase or to stipulate a little bit of what we're saying around, and that's kind of on the gas cooler side of life. If you look at heat reclaim, again, the similar type of thing that we've seen on the air side of life, just now translated into water. So if you look at your typical conventional heat pumps, there's a reason why, like 55 or 65C, in rare cases 65C is the maximum water supply temperature that you can get, where with CO2 you've got the capabilities of taking that water up to 90 degrees C, and that again is typically that same outcome that we just discussed from the air point of view. Although like you can have a system that discharges also at, let's say, 100 plus degrees C, you're going to struggle to get that capacity into your water because there's not as much capacity in your desuperheating part as there is in your condensing part. And then again with CO2, where we have the discharge pressure and the temperature, drop, and due to the non-correlation, you can have your water follow that basically that refrigerant line, or that decrease in the refrigerant line, and get yourself that higher discharge water supply temperatures. So that's the main reason. Again, similar as what we discussed around the gas cooler side from an air point of view and the condenser side. The similar effect happens when it gets to water heating, from a heat pump point of view, and then obviously from a heat reclaim point of view. Then looking specifically at the heat reclaim point of view, what we can consider is, I mean, there's obviously a lot more, but let's say we look at the major ones, like 4 types of heat reclaim systems that we can, or heat reclaim requirements that can be considered. I mean, one can be considered that there is a low quality, low capacity requirement. What we mean with that is, like, you might have within your store or facility, or wherever you have a CO2 refrigeration system operating, you have low temperature requirements and small capacities, meaning your system can probably give you that hot water or that heat that you require without having to manipulate your system. So if you don't have to, you don't have to. So I mean, you can just look at sizing that and getting the requirements that you want. There is then obviously having low quality heat, meaning not necessarily high discharge temperatures, but high capacity. So, I mean, that's going to depend on where your system is running. So you might require a slight manipulation of your system, or in a lot of cases, you might not, if the temperature requirement is fairly low. Then the high quality, low capacity might again require some modification, but not as drastic. And then your high quality, high capacity obviously requires intervening and making your system run transcritical mode. So trying to, how can I say it, bust the myth on heat reclaim between letting your system run subcritical or versus getting the heat that you can require by making your system run transcritical mode. So again, this is a CO2 system operating in transcritical mode. What we did is we just allow for a lot of temperature lines showcasing certain capacities. So when you're running in the subcritical, you can see that you basically can just get from, if you're heating from 21C to 60C or 70F to 140F, you can get maximum 40% of your total THR, and you're running your system at 65 bar for argument's sake. If you force your system to go up to 84 bar, you can get 100% of your total THR, still heating water from 21 to 60C. Going from 21 to 82C, for argument's sake, if you're going to run your system at 84 bar like you did, so when you're heating from 21C to 60C at 85 4 bar, you get 100%. If you need 82C instead of the 60C, so 180F versus the 140F, you need to run your system at 84 bar, you will only get 60% of the total THR versus the 100% you have here. So to get back to getting your 100% capacity, you need to increase your discharge pressure, for argument's sake, to 100 bar. That will give you 100% of your THR with a water inlet temperature of 70F and supplying it at 180F.
And so are you looking to get is it better to have the 100% total heat of rejection? Is that what you're aiming for?
No, that's what I tried, what I indicated from a heat reclaim point of
Yeah.
view. Obviously what you require is what you want to aim for. So
Okay.
if you only require 70F to 140F or lower, and you require 40% or less, then there is no need to manipulate your system, because you
Mm.
can get your heat
Yep.
by operating it normally according to what your system wants to So I mean, if you look at a refrigeration system, if you don't give it any input to tell it you want heat reclaim, that refrigeration system is going to only take care of the refrigeration part of life, meaning the less power you have to put into your compressor versus the maximum cooling that you can get. That's what your system is going to aim for the whole time. So if you can get the heat that you require via optimizing your refrigeration system, basically that heat is completely, totally free.
Yeah.
If you start looking for additional, you start paying small penalties because you're now manipulating your system. But that's why we showcase the next slide. So if you basically going to go and say, so that's what I'm trying to say, like, let's say my system according to ambient is running at 65 5 bar discharge pressure. I'm condensing at 65 bar, but I want 100% THR. So obviously if I run my system, as we said, I can only get 40% of my total THR, and my COP of my system is about 3.66. So where I say what the myth comes in is if you do not have the high pressure valve where you can manipulate your system, the only way that you can increase your discharge pressure, so let's say an HFC based system, if you want to get more heat out of that system, you either need to stop rejecting heat so that your discharge pressure increases itself incrementally, but I mean then your what you would call your condensing temperature also increases.
Mm-hmm.
So you are simulating a bad ambient condition.
Yeah, plug condenser.
With yeah, so with CO2, we don't need to stop our heat rejection. We can still, if we can get a gas cooler outlet temperature of 20 C, because it's fairly nice and cold outside and we're running 65 bar, for you to force that system to run at 80 bar or plus 100 bar, wherever you want to run it, depending on what you need, you do not need to lift or increase your gas cooler outlet temperature. You can still get the 20 C gas cooler outlet temperature, which means your cooling capacity does not go away. You do not reduce or lose your cooling capacity side of life. So the only penalty that you pay is the power that you put into your compressor to run at a slightly higher discharge pressure. But you're not losing the efficiency of the system because of additional flash gas, because there's no additional flash gas. You're, according to your pressure enthalpy diagram, you can still come out as far as you want to the left because of what ambient can allow you. You just increase the discharge pressure. So for that case where we said, like, either we can get 40%, if we want, for argument's sake, I said here, let's say we want a system that naturally is running at 65 bar because it's a nice cold day. I want to heat water from 70 to 140 F. So, okay, if I don't manipulate my system, I can get 40%, I can get 40% of the total heat rejection. And my COP is 3.66. If I go and say, like, hold on, I actually have a need for 100% of the THR. So I want to lift my discharge pressure line. So I need to go from 65 bar to 85 bar, which we all can agree is a fairly high or a fair good increase in discharge pressure.
Yep.
So what that means is if I do discharge myself from 65 to 88 bar, all of a sudden I'm sitting with 100% of the THR, which could fulfill all my need, but my COP drops from 3.66 only to 3.3. So basically I'm paying 10% more for additional power input, but I'm gaining 60% heat.
Wow.
Um,
Yeah. Yeah, that's
so
huge amount.
that's a big amount. So that's
Yeah.
that's why we're trying to say, like, we need to understand we need to disassociate a system running transcritical mode due to ambient conditions forcing you to run there versus you as a user is forcing the system to run there,
Yeah.
but still allowing it to reject heat to the point of the ambient. And that's what you refer to in Canada as a major, is a good example for that. And I mean, your Scandinavia, your northern countries, your cold countries, a lot what you will find that the guys do is they completely bypass the gas cooler. So they will completely bypass the gas cooler or modulate the flow through the gas cooler and they really will put all that heat into whatever their water requirement is, and just reduce that last little bit, like, put a
Yeah.
little bit of your mass flow through that to just make sure that you run as low a gas per outlet temperature as you possibly can before over condensing and doing something
Yeah.
like that, but
That
push
and
all your
what
heat back into your system.
that's so amazing, because when you think of a standard refrigerant, you keep pushing the pressure up, it's making your system less efficient. Even when we talk about hot gas defrost, you can't have low condensing hot gas defrost unless you put a lot of strategy into it, because you need that heat, And so I was not trained, but at first I'm like, okay, well, in transcritical, you're above the point in the middle of the summer, it's using a lot of energy, but now we're talking about winter and you're doing it, manipulating to do that. It's not a big as big of a penalty. So this is what we need to train people and educate people, that
Mm.
in the middle, if you're in a cold climate, pushing into transcritical is not the same as running transcritical in the summertime.
Exactly, and I mean, like we said, to let your system give you to let your refrigeration system allow you for maximum heat reclaim, instead of putting alternative heating sources or requirements. I mean, you can't beat the energy efficiency associated with the heat reclaim out of a system, out of a
Yeah.
refrigeration system, if you still allow yourself to reject your heat to whatever the ambient outside allows you to
Yeah.
do
I,
that.
I was at a system last week, and that's exactly what they had. They had multiple three-way valves from the system going out to an air handler that heated the whole store, which was really cool to see that they're using that to help heat the
Mm.
store. It wasn't running at the time while I was there, but it's something really cool to see, and that to understand it now, that the purpose of doing that is for a different types of energy. And you're saying, 10% power input, but you get 60% more heat. That's huge.
No, it's a big gain. It's worth it.
Yeah.
um,
And it
and I
all
mean, I
depends, once
guess.
again, it all depends on the application. So this is why, and you said it before, it's so important to work with your customer to talk about what their needs are. Because some
Mm.
places, electricity might be higher, natural gas might be higher, whatever it is that you're using to heat. This is a good way, and it could be a good strategy, the way prices continue to go up. If you're using electric heat, prices continue around the world, keep going up. This is a pretty
Mm.
good strategy.
Well, again, I think going back to North America, we're looking at California at this stage where they are looking to enforce getting rid of gas heating and electrifying all the heating. I mean, if you do have a supermarket or an industrial refrigeration system and there is any heating requirements, I mean, if you can't go to your go-to solution anymore, which is tapping into the gas line, you need to look at alternative solutions. So either you're going to look at putting a heat pump next to your refrigeration system, or you can just utilize your refrigeration system.
Yeah.
And I mean, I guess that's another feather in the cap for CO2, is that if you need to electrify your heating and you have heating requirements, CO2 allows you to get that heating, which you can't get with much other refrigerants. And basically, due to critical operation and introduction of a high pressure valve, that allows you to manipulate your system to gain those systems. I mean, I've even seen and have had situations where you can allow for a false evaporator. I mean, where even if, like, let's say you need more heat than what you can gain because of the required cooling capacity, you can turn your refrigeration system, your CO2 refrigeration system, technically into a heat pump. And if you allow for what you would call a false load, and an additional evaporation load, um, or heat source, gain a heat source from somewhere, you can run your refrigeration system part and parcel as a heat pump as well, and just gain that additional heat that you require without having to allow for additional machinery or equipment
Yeah.
or stuff within your facility.
And that's amazing because people don't really understand. Not anyone who's listening and watching, even CO2 heat pumps are gonna blow up, and they're already big, but they're gonna be huge over the next 10 to 20 years. You're going to see this market grow dramatically. If you're in the heat pump industry now and you haven't seen CO2 heat pumps yet, you're going to start seeing them because it just, what we're talking about here today is just so much more, there's so much more characteristics about it where you can gain those extra heat, and the way that it can function with your refrigeration systems. And I see more and more of the bigger manufacturers getting into, and they're already testing CO2 heat pumps. Any of the heat pump manufacturers that you work with now, and you might be using 410A heat pumps, a lot of them are already testing CO2. So learning about this is very important.
No, definitely. Um, I think one last thing that I also could showcase while we're still here is comes down to the same, like we said, the mechanical subcooler. So if you're going to look at a typical system, I mean, this without getting into the detail of this, but let's just focus on this side of life. So if we're saying we've got a gas cooler outlet temperature of 104 F, which is about 40 C. So typically if you don't have any additional subcooling requirements, or you're just literally you are operating on a gas cooler outlet temperature of 40 C or 104 F, your optimum discharge pressure will be around the 98.6 bar. So we can just go and say 98.6 bars. So sorry, I just want to let's make that the same, 98.6. Wait, oh, 104. I'm confusing myself here.
Yeah.
So if you make it the same, as we can see, like your mechanical subcooling input requirement is 0 kilowatts. So what I'm trying to say, like if you control your systems on the gas cooler outlet temperature, meaning your controller is going to see 104 F or 40 C gas cooler outlet temperature, and it's going to tell you I need to run at 98.6 bar because that's my most efficient, how can I say it, discharge pressure according to gas cooler outlet temperature. So if we throw a mechanical subcooler onto that and we go and say like, okay, take me from 140 F to, I don't know, let's see here, what is a round number? So 40 to, let's say we want to go to 36, so 96.8. 96.8. You can see that is the effect that the mechanical subcooler brought for you. So that point there was indicating, sorry if I can just move.
Yeah, so you're pushing the enthalpy line, you're condensing a gas cooler line further to the left. So the further you can
Yeah,
push that to the left is that means there's less flash gas happening.
yeah. I just want to give you guys a little bit of a closer look to that. So yeah, so that was your original gas cooler outlet temperature. So you would have come down here. So exactly to what you're saying, you are reducing it further and you are reducing less flash gas. So end of the day, that's the gain that you do. What we see a lot is the guys go and say like, well, my new gas cooler outlet temperature is 36. My energy saving sits in the compressor power. So a lot of times that we've seen the mistakes being made is to go and say like, okay, well, my new optimum discharge pressure should be 88.8. But remember 100 kilowatts for your mechanical subcooling, 88.8. If you do allow your system to drop and you want the same gas cooler outlet temperature of your mechanical subcooler, all of a sudden you need 239 kilowatts from your mechanical subcooler. So that's why we say it's always better to control on your gas cooler outlet temperature
Yeah.
and get your energy saving out of exactly what it's called, the mechanical out of the subcooling of life, and not by reducing your discharge pressure.
Yeah.
So I mean, that's as simple as where we've had guys complain that saying that mechanical subcooling does not work, and all that you ask them is, where's your gas cooler outlet probe? Is it before or after mechanical subcooling? And if it's after, you got a problem. If it's before, you're okay. You will
Yeah,
get the benefit out of it.
that
So
should be right at the outlet, depending on the manufacturer. It should be, like 7 or 9 o'clock. Insulate it really well, tight against there. So the sun doesn't get on it, and you want to check with the manufacturer where they put it on their equipment. It's very important. That is the key to most CO2 systems is that the gas cooler temperature probe. So make sure you put it in the
Mhm.
right location. If you don't know where it's at, follow up with the manufacturer of that equipment and ask them exactly. Because all of them, I've been reading lots of their manuals, and a lot of them have pictures in their manuals showing exactly where it goes.
Yeah, and I mean, and especially if you have a small system, like let's say your gas cooler and everything is quite compact, you really want to make sure that you don't have that gas cooler outlet probe close to your high pressure valve, because remember you have a temperature difference across your high pressure valve, which is fairly big, and that can migrate up the line
Oh, that's a good point.
on the gas cooler side of life, and you might have a false gas cooler outlet reading.
Yeah, that's
So
a
that
great
also
point.
that also can happen.
So I never even
Um,
thought of that because yeah, you're taking could be 1400 psi, 100 bar, whatever it is, and you're reducing that pressure down to 550 psi or whatever, 34 bar. It doesn't matter. That's such a
mm.
huge pressure drop. That makes so much sense that it could. Yeah, that's awesome. That's good to
No, you
know.
can get some temperature migration, especially if you have it very close. I mean, if you have it going to be have the gas cooler outlet temperature probe sitting right on the inlet of your high pressure valve, you might not get the right
Yeah,
reading
it's
that
good to
you
know.
are
Great
looking
tip.
for.
Great tip.
So yeah, I think that's I mean that's the interesting thing that you can get these little things that you can play with if you do utilize um, like I said, like if you do play and gonna go and start designing from this, I mean, the one thing that I can really attest to is that every time you do a system, you learn something new. When you try something, there's something that sometimes it even is that you maybe make a mistake in your like in your programming or in the writing of the program, and to figure it out, you still learn a lot. I mean, another thing that you can look at is maybe that like if you do allow for an LTD superheater, so um, I mean what you can do with this program is you can literally go and see what your temperature would be if you once you've mixed all your lines, because what you need to remember in a booster system, you've got leading up to your medium temp compressor, if you have a large LT capacity requirement, there's a big mass flow coming back, and you've got LT compressors discharging at, in this case, up to 40 50 C 118 F discharge out of that LT compressor, and that can be higher. I mean, that superheat is
Yeah,
fairly low, 15K, so that can be even higher. Um, so leading up to your medium temp compressor suction, what you need to remember is you either have flash gas, which has a certain mass flow and a certain velocity and a certain temperature. You have your medium temp evaporation side that has a certain velocity, a certain temperature, and you have your LT side of life, which has a certain velocity and a certain temperature, which all mix into the and eventually end up going to the suction of your empty compressor, which at the end of the day, you want to have a specific or a certain type of superheat at that medium temp compressor. So a lot of times, having an LTD superheat that has multi-functions to go and say like you can reduce or increase or control the LT discharge temperature to a certain degree according to what your ambient is, um, to kind of help and control on your medium temp side of life on your superheat of your compressors, um, before you start adhering to either hot gas injection or liquid injection to control your superheat side of life. So that's also another measure of looking at controlling your overall system superheat.
yeah,
And that you can look at here and go and play and see like my 85F, there we have -1C at the compressor. So if I'm gonna say I'm doing no heat rejection, so I make my desuperheater the same as the outlet temperature, your -1.1 becomes 0.4. So you gain some superheat there.
yeah.
So that's all the kind of stuff you can play with, and gain
Where
some
where can people
insights.
find this software if they want to use it? Do they just go online to look it up, or how would
No, it's
people?
unfortunately paid software. Yeah, sorry, I see there is some questions if you maybe want to look at the chat. Um, it's a paid software.
Yeah. So yeah,
Through
look.
I think it's a Danish. It's a
that's
Danish
fine if it's
company.
paying. That's paying software. That means there a lot of times there are better softwares, right? You pay for what you get, and it looks like this software here. I know that you believe in this software. You use it all the time. It has to be one of the go-to software. So you can look it up. EES Professional Software. We do have a question in the chat that we'll get to. Is the mechanical subcoolant value the penalty that you have for trying to run too low a flash tank pressure? Penalty that you'll have to pay. Hmm.
I'm just trying to understand too low flash. So no, the flash tank pressure. So one thing you need to understand, what we need to. So okay, so let's look at a flash tank pressure. So the flash tank pressure at the end of the day doesn't have a massive effect on your overall system efficiency. All that you're doing is if you increase your flash tank pressure, I mean, you can look where's the flash tank pressure. Sure, we've had it here as an input there. So currently it's at 38 bar. So you can go and see if we make that, for argument's sake, 42 bar. All you're doing is you're increasing your discharge pressure. So what you're doing is you're creating a little bit of less flash gas, but all you're doing is you're moving that flash gas to your evaporators. So you're still paying a penalty if you not you're moving the penalty from one place to another. So I mean, because you're not changing where you come down, you're not changing your gas cooler outlet of where you come down. So I mean, if you take that back to 38 bar again, you can see your line stays where it is. You're just dropping this line, meaning you follow down this, you follow more to the left. So you have more flash gas in your receiver tank, but you have less in your evaporators. So that's a question I think you asked earlier as well, Trevor. And basically, what I can say from an input from, let's say, if you look at a normal transcritical booster operational system, the receiver pressure, the only place that it comes down to is what I say is what you need to keep into consideration is your MOPs. So for me, it's you've got an MOP over your high pressure valve and you've got an MOP over your electronic expansion device. So you need to make sure you have enough pressure in your liquid line that your electronic expansion valves are maintained or remain operational.
Yep.
And you obviously have a MOP over your high pressure valve. So the lower the higher your receiver pressure, the higher your allowable minimum discharge pressure becomes. The lower your receiver, the lower your allowable minimum discharge pressure becomes, meaning that you can gain a little bit more out of your cold environments. And you can gain your efficiency in the cold environments without having to cap your minimum discharge pressure at a certain value because of an MOP of a valve.
Yeah. No, perfect. That's very important to understand MOPs, so the maximum operation pressure of these electronic valves, because there is a certain pressure that you need them to function. Because if it gets too high, maybe that valve will not open or close. So it's very important to understand that stuff. Because when I first got into electronic valves, I didn't really understand what MOP was. I seen it in the controller in the program until when I started seeing valves not working because that pressure was way too high, and so and it can affect it. And just so everybody knows, when we're talking about mechanical subcooling and CO2 systems, especially on a transcritical system, it's different than when we're talking about mechanical subcooling on a standard HFC rack. On a standard HFC rack, we're trying to cool down the liquid going out to your cases. So you have a cold or liquid going out to your cases. When we're talking about mechanical subcooling on a transcritical system, we're trying to cool down that gas at the outlet of that gas cooler condenser so we have less flash gas in going into that flash tank receiver. Because you have a less flash gas, that's less work on that system. Did I say that right, Wynand?
Yeah, and that's basically, so let's put it, mechanical subcooling can be a high ambient strategy, the same like you have with ejectors and parallel compression and stuff like that. So it depends on what you're doing. So it might be that you have a chiller or a cooler system or something somewhere, or a dedicated system for that matter. But yeah, I guess a lot of times the misconception that we have is people do think that you might add a subcooler to try and reduce the discharge pressure, but it's more about getting the maximum. By reducing your gas cooler outlet, you reduce the amount of flash gas within the system.
Yeah.
And that the less flash gas, so I mean, flash gas is, you can't do any work. You've got, so remember, you can't change the mass flow of a system. The mass flow within a system stays constant, according to where you're running and stuff like that. Let's say you don't change anything at the low side of life, so fairly your mass flow and what you pump around stays constant. So if you generate more more flash gas, you've got a majority. I think we can see it here. Let's go back to the, sorry, last time we said 104, 98.6, 98.6 calculating. So let's make this 104. So let's say we have no mechanical subcooling. So our flash gas, our mass flow of our flash gas is 2.84 kilograms per second, or 22,500 pounds per hour. Just trying to see, and your system, so your system mass flow is 5.9, which is going through your gas cooler. After it goes through your high pressure valve, you generate, so the mass flow here is 5.9. After your high pressure valve, you drop into your two-phase region. So now out of that, 2.4 kilograms per second is actually liquid, and 2.84 of that, so more than 50% of your mass flow into your receiver is flash gas. And that flash gas just goes straight back to your compressor. It does no work. There's no work in flash gas. If you don't change phase, you can't work. So if you take your mechanical subcooling now and you go and say like, okay, cool, what we said is we want to go from at least 40 to 36, which is 96.8. 6.8. So let's just remember we had 2.8 flash gas, 2.4 liquid. So if we introduce that, we don't change the pressure. We go from 1.9 flash gas to 2.4 liquid.
So a huge
so all of a
reduction.
sudden you swing it around. Now at least your liquid is more than your actual flash gas. So you've got more liquid to do cooling. That's where your capacity, that's where your cooling capacity is. Before anybody wonders, that figure will stay the same, because I am basically telling the system what my cooling capacity are.
Yeah.
So just, if anybody wonder why the liquid mass flow don't change, just in this program I fixed my cooling capacity requirement. So the flash gas is the only thing that will change.
And that was something that really blew my mind when I was first working with Andre Patnaud from Emerson, learning about this. He was like, you know, in the middle of the summer, you design a system in Canada and you have 10 transcritical compressors, and 5 of them are running just to digest that flash gas. And in the middle of the winter, you don't need those 10 compressors. And this is why mechanical subcooling, parallel compression, adiabatic cooling, injectors, high ambient strategies are in play, is so you don't have to design systems with so much non productive work or non-useful work from this flash gas. So it's super cool to see that and actually see the numbers, because that's a huge reduction with just a little bit of subcooling. We just went from 104 Fahrenheit down to 96.8 Fahrenheit. That's just a little bit.
Yep. Yeah, and it's a massive reduction in your actual, your mass flow of your flash gas valves.
Yeah, I love this. I learned so much, Wynand, and I really appreciate you taking the time. Why don't you let everyone know again where they can find you if they want to learn more about you, your company, this software, because you definitely help many companies around the globe get into the CO2 game, and they're becoming very successful. So please let everyone know where they can find you.
Sure. You can find me on LinkedIn, or otherwise you can find me at Wynand at futuregreen.co.za. So that's WYNAND at futuregreen.co.za. Or on our website, Future Green Now. Feel free if there's anything we can help out with.
Awesome. I want to thank you for your time. I want to thank everyone. I thank the whole audience. I really appreciate all of you taking the time to hang out with us today to talk about this, learn a little bit about CO2. I'm super excited to have all of you wanting to learn a little bit about this stuff because I think it's very important to increase and invest in yourself. Thanks again, Wynand, and I'll see you at the next CO2 Monday, everyone. See you later.
Thanks, everyone. Have a good day.
Hey, I want to thank you for taking the time to watch this video. I hope you got something out of it, something that you can use in your daily life. If you like this video, hit the thumbs up button, hit the subscribe button, and click the bell button because when you do click the bell button, it will notify you anytime new videos are released. Also, check out the Refrigeration Mentor webpage at refrigerationmentor.com where I'll have all the different trainings, upcoming events, the different podcasts I've been on, as well as the Refrigeration Mentor podcast. If you want to check that out on Apple, Spotify, Google, any service provider of your choice. Super excited to see you at the next video. Now let's get a conversation going.